Today we'll see the problem. Find the city with smallest number of neighbors at a threshold distance. Okay, let's go through the problem statement first. We are given n cities numbered from 0 to n minus 1. Given an array edges where edges of I equals to from I to I and weight of I. What they represent, we'll see. They represent a bidirectional and weighted edge between cities from I to 2I, given the integer distance threshold. What we need to return the city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. If there are multiple such cities, return the city with the greatest number. Okay, what actually they are asking, what they are actually telling, and what they are actually asking, we'll see. We will be given n, which means there are n0 to n minus 1 cities. Okay, 0 to n minus 1 cities, total n cities, and they also give us edges, which means from, if you see here, from 0th city to first city there is a distance of 3, and they have also mentioned that it's bidirectional, which means you can go from 0 to 1 and you can also go from 1 to 0. Bidirectional is represented as like this. You can go from either direction. Okay, you're getting it right. So that's what bidirectional means. And you see here, we are told to give, we are told to return a city with which we can go from this city to other cities, this city to least number of other cities. Okay, if there are n cities, 1 0 1 2 3, you can go from these cities to other cities. From 0 you can go to 1, and from 1 you can go to 2. So from 0 you can directly go to 2, and from 1 you can also go to 3. So you can directly go from 0 to, and 0, from 0 city you can go from 1 to 3. How you can go 0 to 1, and from for 2 0 1 2, and for 3 you can go like this, 0 1 3. Okay, in whichever way you go, you can reach the city 1 2 3 from 0th city. So they want a city where it can reach least number of cities, and the distance from this city 0 to city 1 should not be more than threshold distance. Okay, should not be more than, less than or equal, should be less than or equals to 4, should not be more than 4. For each and every question they will be mentioning the threshold distance. Okay, that's what we need to check. For this, let's go to the intuition. We will have a distances matrix which will keep track of distances of each and every city. So if you need to make a n cross n matrix, n cross n, what you will do, 0, you put everything with highest number, infinity. Let's take the same here. If we take, it should be 4 cross 4 matrix, infinity. So infinity, 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 infinity. Okay, we will fill the matrix with infinity. Now what we'll do is, we will update the distances matrix based on the distances which we get. But now we'll try to update the distances matrix from going to 0th city. From 0th city takes nothing, you'll be in that particular city, right? So the distance is 0. From going to that particular city, from that particular city is no sense, so we'll put it as 0. What does this matrix say is, this is city 0 1 2 3, this is city 1 2 0 1 2, 3. What did it say? You are going from city 0 to city 0. You're going from, sorry, you're going from city 0 to city 0. You're going from city 0 to city 1. You're going from city 0 to city 2. You're going from city 0 to city 3. You are trying to keep track of all the distances. Okay, from city 0 to city 0, it makes no sense. It's zero distance. You're being in that city and calculating the distance from that city to that city is 0. So that's what we are doing here. We are putting it as 0. Okay, you're getting it right. And now what we'll do is we'll try to do a the we'll try to find the shortest distances from this particular city to all the other cities it can go. Okay, we'll try to get the shortest distances. For that I'll use Dijkstra's Dijkstra's algorithm. What is this? A single node shortest path algorithm. This is how it will be done. I'll just show you. You will take a priority queue. Okay, how the priority queue will be used and what are the distances. Let's take shortest path algorithm for 0th city. So from 0 to 0, 1, 2, 3. These are the cities it can go, let's suppose. So at first it will be infinity, 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 and 0. We'll take it from this particular distances array. Okay, we'll give it the same row. For the distance, the city 0, we'll be providing the 0th row of that particular distances. Okay, now what we'll do, for 0, we'll add this particular 0 into this priority queue with the distances is 0 and the node is 0. The first is distance and the other is, I mean, city. Okay, now what we'll do, I'll pop this. You'll get queue becomes 0, empty. You'll get an output pop. After popping it is 0 comma 0. From this I'll get the adjacency list of zeros. What does adjacency list mean? You're given the edges, right? From this you need to create an adjacency list. I'll write down this particular thing. Edges equals to, they have already given 0 1 3 1 2 1 1 3 4 2 3 1. Okay, these are the edges which they have given. Now what I'll do is adjacency list equals to, for each and every city you'll find the adjacency list. You'll create an empty adjacency list with n cities. Okay, for each and every city iterate through edges for I in edges. So add it. For 0th city you can, from 0th city to first city the distance is 3. So what I'll do is adjacency list of I of 0 dot append. What I'll append, I have already told you, we will be using this format. First we'll give the distance and then the city name. So the distance is 3 from 0th city to first city, it's 3 and the city is 1. You're getting it right? For the first one, now the adjacency list becomes is 1 3, and also we'll update the second one. I of 1 dot append, if we generalize this is I of 2 comma I of 0 here, and if we put a generalized equation here it is I of 2 comma I of 1. Okay, this will create an adjacency list. In this, what will be the adjacency list? If we see, at the last will be, for the 0th one, it will be 1 3 1. Okay, and this is for 0th. For the first one, it will be 0 3 0, and 1 can go to 2 with a distance of 1. So distance of 1 for node 2, and 1 can go, and we'll give it for 2 as well. Distance of 1 for node 1. Okay, and for 2 to 3 with the distance of 1, so it can go to, oh sorry, I missed this. 1 to 3 with the distance of 4, it can go to 4 3. 3, it can go to 1 with a distance 4 with the distance, it can go to 1 with a distance of 4. 3 can go to 1 with a distance of 4. That's what it means, right? 1 to 3 4 distance is 4, 3 to 1 distance is 4. That's what I am writing. 1 to 3, 0th index, 1 index, 2 index, 3 index, which means 0th city, first city, second city, third city. From 0th city you can go to first city with a distance of 3. That's what I written. Which you can go to distance city 1 with a distance of 3. I'm following this particular format. We'll first indicate in distance and then city. Okay, and here they are saying you can go from 1 to 2, 2 to 1 with a distance of 1. 1 to 2. See, you can go to 2 with a distance of 1 from 1. Okay, that's how I am trying to update the adjacency list. If you see here, the from 3 I can go to 1 with a distance of 4. uh, 4, this is where. From 2 you can go to the distance, you can go to 3 with a distance of 1. That's what I've written here, and I'll also update here. You'll go and go to 3 with a distance of 1. Okay, this is the adjacency list we'll be getting. You can even verify that. 0 can go to 1, 0 can go to 1, and 1 can go to 0. So 1 can go to 0, 0 can go to 1, 1 can go to 0, and 1 can go to 2, 2 can go to 1, 1 can go to 2, and 2 can go to 1. I am updating the distance here and here. Okay, the format is this: distance and city. You can use any other for whichever format you want. You can use city first and distance second. It's your wish. I'm using this way. Okay, once after this adjacency list is done, I'll use it here. See, now what I'll do is, once we come back, we have a priority queue added. First it will be like this: whatever if you are trying to get the shortest path distances for city 0, then priority queue will be with node city 0. The distance from this is 0. So that's it. Now what we'll do is we'll try to pop this out, so it will become empty. We'll have 0 comma 0 out, and we'll get the adjacency list for this particular city. What's the adjacency list for this particular city? This is adjacency list of 0 is 3 comma 1, so you'll add 3 comma 1 here. Okay, the distance here is 0, so 0 is already there, so we don't update the distance in the particular array. Okay, but then you will add 0 to 0 plus 3 here. It's anyway 3, so we are not going to update it. Okay, now what we'll do is we'll again pop it. What it will be? 3 comma 1. Find the adjacency list for this particular one. What's the adjacency list for this particular one? This is the adjacency list. Write it there. and the distance is 3. So 3 plus 3 comma 0. Okay. 3 plus 1 comma 2. 4 comma 2. I'll write 3 plus 1 only. 3 plus 1 comma 2 and 3 plus 4 comma 3. 3 plus 4 comma 3. Okay. We are trying to update the priority queue. We have popped this, so it will go out. After popping only we are adding it. So that's why we'll have only 3. And now we'll check. We'll add this to the visited queue. Why this is used? Once we have visited, and mm, we also need to make sure that it doesn't form a loop, right? So we try to have a visited set which will keep track of all the nodes which have traversed till now. So we have already traversed 0, so we'll set will already have 0. Whenever we pop, we'll directly add it to the uh, visited set. Okay, we have already popped 1 as well, right? We'll add it to the visited list, visited set. I mean, now the set will have visited set will have 0 1. Okay, now try to update. See, from 0 you can go to 1 with a distance of 3. You will update 3 here. That's what we popped and got it, right? We'll update there. Now what we'll do, we'll pop the least distance thing. Here the least distance is for 2. For the city 2 we can go in least distance, because the distance here is 6, the distance here is 4, and the distance here is 7. If we add the uh, previous distances and the distance from this particular node 1, it becomes 6, it becomes 4, it becomes 7. You're getting it right? So 7 4 6, which is least 4. So we'll pop this first. We will use a priority queue puts this in order. It maintains the minimum value first. So when we pop it, we'll directly get this out. What is this? 4 and 2. Okay. What we'll do is we'll remove this and we'll add the adjacency list of 2. 1 1 1 3. We'll add it here. The distance here is 4. 4 plus 1 comma 1. 4 plus 1 comma 3. Okay. Now check the minimum distance which we can go. So 2 has the minimum distance 4. We'll update it there. And the threshold distance they have provided is also 4. Okay, so we have already reached threshold distance. Okay, now we'll try to pop anything. What will pop? If you see here, the distance is 5. The distance is 5. If we try to pop, the one out of this will get, whichever is added first will come first. Okay, so if you think this has come first, one is already in the this, we can add 2 as well because we have popped it. So if one is already in this list, so nothing we can do. And again we'll pop 3. If you see, the distance is already greater than threshold, so we will not add the adjacency list of 3. You're getting it right? So because we can go to city 3, but the distance is getting more than threshold. That's how we'll try to update the shortest path for this city 0. We'll do the same for city 1, city 2, and city 3 as well. You're getting it right? And then at last we'll try to calculate how many cities are there for city 0, how many cities we can reach from city 1, how many cities we can reach from 2 and 3 as well. And we will return the city with the least number of cities we can go. And if there is any tie, we'll give the largest number. You're getting it right? Okay. We'll see the code now. We'll create a matrix named as distances to keep track of distances okay, name it as distances. What I'm doing is, what does this matrix represent is distance from city I to city j. We'll try to find the distances from city I to city j. So we'll try to store it in this particular variable. Okay, now I'll try to find the adjacency matrix. Adjacency list is empty as of now for I in range of n. I'll iterate through edges. I of 0 dot append I of 2 comma I of 1. You can see, as this is bidirectional, I will be doing the same in other direction as well. And we are here using the format first distance and then city. That's why I of 2 and I of 1. And then we got the adjacency list, we got the self-dot distances, and we need to put self-dot distances of I equals to 0, which means distance from city A to city I to city I. City I. So the distance from the same city to the same city is uh, 0. We are doing that. Now what we'll do is, we'll do BFS. What here BFS means, the shortest path algorithm, which is Dijkstra's, which uses BFS in it. So I was just naming it as BFS. So what I'll do is, I'll have a queue in it, and heap phi with distance 0 and the same city. We'll start with that city, and we'll try to get the shortest path from the city to all other cities. Okay, while the queue is not empty, we go through it, pop it from the heap pop of queue, and try to, we'll have a visited set to keep track of visited dot add k of 1, and let's keep distance as k of 0, and check if distance is less than or equals to threshold distance. If so, go inside it and update the distances variable. How will we updating it? Self dot distances of city and k of 1 should be minimum of this and distance. Okay, if so, update it. And now what I will do is, for I in adjacency list, I'll iterate through the adjacency list of this k of 1. If I get the adjacency list of k of 1, if I of 1 not in visited, I'll heap push you with this particular city. Distance plus I of 0 comma I of 1. Okay, updating it. Okay, we'll try to call it and call BFS of city is 0. Start with I and city visited is set. Now print self dot distances. I'll print as of now. I'll return 0. I'll run this. What's this? Oh, there's a dot here. It should not be there. I'll run this. If you see, the distances are getting updated. Now we'll try to count how many of them are there. We'll have a dictionary for the result. Result equals to dictionary, and now of I equals to, we'll have a function count cities of x. We'll have a count equals to 0 for I in x if I less than or equals to distance threshold. If then count plus equals to 1, return count. Okay, count of count of will send this particular self dot distances of I. Okay, we'll update it. Mm, and now we'll print result and we'll return list of result dot keys of 0. Okay, if we say for um, what's result 4 and 4, what's self dot distances, what is self dot distances, print self dot distances. Okay, okay, this is done. I'm getting it right, but then I need to sort it. Result equals to dict of sorted of result dot x equals to x of 1. Okay, now I'll run this. We hit fast 0 and 0. Okay, we'll submit this. See, solution got accepted. If we analyze the complexity, it's n square log n. Got it right? Okay, that's how it's done. If you have any questions, please comment them in the comment box. Please like, share, and subscribe.